So this week we're going to be learning a little bit about stoichiometry and how to calculate mole-to-mole problems and mass-to-mass problems. And we're going to go through just review strategy for balancing chemical reactions, because that's kind of the first step to being able to do a stoichiometry problem, is making sure your reaction is balanced. So I've listed out some steps that you can follow to have a strategy in place for balancing chemical reactions. And so the first step is to write out the unbalanced reaction. And so here I have a word equation, and I want us to practice real quick, or see real quick, how to change a word equation into a chemical equation with chemical formulas. So let's review that real quick. All of these compounds in this reaction are ionic compounds, and we'll have to remember that for ionic compounds you have to balance their charges. So we have magnesium nitrate, potassium chloride as our reactants. Let's remember that every element in group 2, such as magnesium, has a charge of +2. So our ion for magnesium will be +2. Potassium is found in group 1, and all of our group 1 ions are +1. And then chloride is just the ion of Cl, and since it's in group 7, it gains 1 electron and has a -1 charge when it is an ion. And nitrate is actually a polyatomic, so you'd have to find it on the back of your periodic table, and if you look, it also has a -1 charge. So magnesium nitrate then should be balanced between our +2 and our -1. If we remember the crisscross method, that means I'll have 1 magnesium and 2 nitrates. So it'll be MgNO3. Whenever you have 2 polyatomic ions or more, you have to put it in parentheses and put the number outside. So that's magnesium nitrate plus our potassium chloride. Each of these have a 1 charge, so it'll just be KCl. Those two things are going to go to make potassium nitrate and magnesium chloride. Now, we know this is going to be a double replacement because we have ionic compound, ionic compound. So essentially all that's going to happen is magnesium is going to join up with chlorine, and nitrate is going to join up with potassium. So we will have MgCl2. The reason it's Cl2 is because it's this -1 charge with a +2, and we've got a crisscross. And our potassium will be with 1 nitrate, so KNO3. Okay, all right. I'm going to change colors because it's kind of hard to see on the red background. But once we do that, we have our unbalanced reaction. We have to figure out how can we make this balanced. So we know that we're going to have an easier time if we go ahead and tally everything up. So we've got our reactants over here. We've got our products. Alright. And I'm going to tally this up. So we've got magnesium is 1 piece, nitrate is 1 piece, chloride is 1 piece, and potassium is 1 piece. So on this side, we've got 1 magnesium, 2 nitrates, 1 chlorine, and 1 potassium. On this side, we've got 1 magnesium, 1 nitrate, 2 chlorines, and 1 potassium. Okay, so clearly we're going to need to modify our number of nitrates because these are not balanced. We need to modify our number of chlorides because these are not balanced. So to change 1 nitrate into 2 nitrates so it'll balance with that one, we just got to multiply by 2, which when we multiply this compound by 2, that'll give us 2 nitrates. So not only does that give us 2 nitrates, it also gives us 2 potassiums. So we can change our number of potassiums to 2 now. So now we've got 2 of everything on the right side except for magnesium. Let's see if we can do that to the other side. Change our chlorines to have 2 and our potassiums to have 2 in the reactant side. In order to do that, all we have to do is multiply by 2, and we can do that by putting a big 2 out in front of potassium chloride. And that's going to actually fix both of them at the same time. So now this will be our balanced reaction. 1 magnesium nitrate with 2 potassium chlorides makes 1 magnesium chloride and 2 potassium nitrates. Alright, so to look at stoichiometry, we need to start out with the idea of mole ratios. And this is very similar to a recipe for some food item. And so here I'm going to use a hamburger as our food item we're looking at. So basically, if I gave you a recipe for a hamburger and I said that requires 1 bun, 2 hamburger patties, 2 slices of cheese, and 4 strips of bacon, you would put all these things together and you would have your double bacon cheeseburger. Now this would be like a synthesis reaction because we're taking a whole bunch of pieces and putting them together to make one thing. So if I have my recipe and I then ask you the question, if I make 5 double bacon cheeseburgers, how many hamburger buns did I use? Well, we know that to make 1 double bacon cheeseburger, we needed 1 bun. So for 5 double bacon cheeseburgers, we should use 5 buns. Okay, and then for the question about how many strips of bacon we needed, for 1 double bacon cheeseburger, we needed 4 strips of bacon. So however many cheeseburgers we make, we're going to have to multiply it by 4 to find the number of strips of bacon. So if we make 5 cheeseburgers, 4 times 5 would give us 20 bacon pieces. Alright, so we can use our recipe like that. And this is actually something that we're going to look at in a second, which we'll call a mole ratio. We can see this actually in a chemical reaction the same way. A chemical reaction, once it's balanced, is kind of like a recipe. So this recipe here says 1 sulfuric acid with 2 sodium hydroxides reacts to make 1 sodium sulfate and 2 water molecules. So the same question, if I wanted to make 5 moles of sodium sulfate, how many moles of sulfuric acid would I need? Well, since this is a 1-to-1 ratio of sulfuric acid and sodium sulfate, to make 5 moles of sodium sulfate, I would need 5 moles of sulfuric acid. Now the next question is, okay, if I need 5 moles of sodium sulfate, and I want to know how many moles of sodium hydroxide I would need, well, for every 1 sodium sulfate, there needs to be 2 sodium hydroxide. So therefore, we would need 10 moles of sodium hydroxide to be able to make 1 mole, or 5 moles of sodium sulfate. Okay, so if we wanted to write these out as mole ratios to see how this calculation works out, this will actually make our life a little simpler. Because you're not usually going to get an even whole number like 5 for the number of moles. Here we have the question 2.35 moles of sodium sulfate. How many moles of sulfuric acid would I need? Okay, so we're going to write this out with mole ratios. Basically, all we do is we take the numbers in front of each compound in the reaction and we change it into a mole ratio. So for our first one here, we're going to be converting between sodium sulfate and sulfuric acid. So I'm going to take this and this to make a mole ratio. Basically, I can put whichever one I need on the top and whichever one I need on the bottom. So I can have 1 mole of sulfuric acid on the top with 1 mole sodium sulfate on the bottom, or vice versa. I could write it either way. Whichever way is going to allow me to cancel out what I'm converting away from. So I'm going to put my given information here, which is this 2.35 moles. I want to convert away from that number of moles of sodium sulfate. And I want to achieve moles of sulfuric acid. So that means I'm going to put my 1 mole sulfuric acid from the 1 given in the balanced reaction in the numerator. 1 mole H2SO4, because that will be the new unit, essentially. You can treat that compound like it's a unit. And our old unit of sodium sulfate will be canceled out when it is in the denominator, because we got moles of sodium sulfate over here divided by moles of sodium sulfate, it'll cancel out and we'll be left with sulfuric acid. And since it's 1:1 ratio, we're going to still end up with 2.35 mole of sulfuric acid. Okay, so this is going to look a little different when we get to the sodium hydroxide in just a second. So if we do the same thing, and instead of using sulfuric acid for the thing we're changing to, we use our sodium hydroxide, we can write the same thing out, 2.35 mole of sodium sulfate. And we're still going to put our sodium sulfate in the bottom, and it's still 1 mole of sodium sulfate because that's what the recipe calls for. In our balanced reaction. But now in the numerator, we're going to put our 2 moles of sodium hydroxide, because that's what our recipe calls for. Oops, oh yeah, NaOH is sodium hydroxide. So when we actually do this calculation, instead of just keeping the same number, now we have 2.35 times 2 divided by 1. So that's essentially the same thing as just multiplying by 2, which when you take 2.35 and multiply by 2, it should be 4.70, I believe, mole of sodium hydroxide. Okay, that's how to use a mole ratio to convert from moles to moles. All right, so in our reading for this week, you've seen a little bit about single-step stoichiometry and how we can use this to be able to do any type of stoichiometry problem. Okay, so this is a method that Dr. Oko came up with, and it's pretty genius because it makes the lives of students much easier if you understand how to use it. So basically, we can take this chemical equation and we can interpret it to mean however many molecules are involved, however many moles of each thing are involved, and however many grams of each thing are involved. And we're going to go through that real quick, and I'll probably have to actually work some problems using this in the next video. But if you think about how this reaction is balanced out, this should kind of line up with how we've seen the simulations, and you should be able to visualize this if you look back at the notes. To see this reaction, because it's balanced with 2 hydrogen molecules reacting with 1 oxygen molecule to make 2 water molecules, when we look at the particulate level, which means how many particles are involved, we would have 2 molecules of hydrogen gas reacting with 1 molecule of oxygen to make 2 molecules of water. And we got this from the balanced reaction. Now the same thing can be said at the molar level. 2 moles, which are a ton of molecules involved, but we're only caring about moles at that level. 2 moles of hydrogen at molecules will react with 1 mole of oxygen molecules to make 2 moles of water molecules. Okay, so that's now interpreted at 2 different levels. Now the only one that gets complicated is when we get to the macroscopic level, which has to do with how much mass is involved. And you'll need your periodic table for this. So I'm going to kind of leave whole numbers and stuff here because I don't want to worry about decimals since I don't have a calculator with me. But first you calculate the molar mass of the compound. So H2, that means 2 times the mass of hydrogen, which is 1. That gives you 2 grams. But not only that 2 grams of the H2 molecule, there are 2 H2 molecules, so multiply that number by 2, and you get 4 grams. So I'm going to write 4 in the table for hydrogen gas. Once we get to oxygen, we've only got 1 oxygen molecule, but there are 2 oxygen atoms in 1 oxygen molecule. So 2 times the mass of oxygen atom, which is 16, will give us 32 grams of oxygen. And finally, we get to water. 1 water molecule has 2 times that 1 gram per hydrogen plus 16 for oxygen. So 1 water molecule weighs 18 grams. But if we have 2 water molecules, 2 times 18 will give us 36. So 36 grams of water. And we'll get to the actual stoichiometry problems using this table in the next video, which hopefully won't be too long. But that's how to fill in the table, and whenever you get to a problem and it gives you a chemical reaction that's balanced, go go ahead and fill out this table.